Hey everyone, welcome to another explainer. Today, we are shining a spotlight on a foundational engineering concept that literally governs almost every single physical interaction in our world. Yeah, we're talking about friction. It's this invisible, everyday force that's happening all around you, right at this very second. It shapes how objects move, how our machines operate, and honestly, how you even manage to drag yourself out of bed in the morning without just sliding right onto the floor. So let's just dive right into this by asking a pretty fundamental question. What exactly is this invisible force that allows you to walk down the street without slipping everywhere, but simultaneously and kind of secretly steals energy right out of the engines of our cars? It's this wild paradox of physics that engineers have spent centuries trying to master. Which brings us to section 1, the invisible force. Let's get a basic intro to what friction actually is. Okay, so in engineering mechanics, when there's a tendency for two contacting bodies to move relative to one another, friction is the reaction force that steps in. And here's the golden rule you got to remember. Friction always acts in the direction that opposes that tendency to move. If you push forward, well, friction pushes backward. It is basically nature's way of resisting motion. Notice how the applied force pushes the block to the right. Instantly, the friction force appears, acting entirely tangentially along those contacting surfaces and pointing exactly opposite to the applied force. It's essentially a direct horizontal tug of war. So, along with the normal force pushing up from the surface beneath it, this simple free body diagram represents the core battle happening every single time objects touch. But you gotta keep in mind, this invisible force isn't just some constant, unchanging number. Its magnitude relies heavily on the physical characteristics of the objects involved, specifically how rough the interacting surfaces actually are. I mean, even surfaces that feel perfectly smooth to the touch, like a pane of glass, look like jagged mountain ranges under a microscope. So naturally, a sheet of ice and a sheet of sandpaper are going to generate wildly different magnitudes of friction when you try to slide a block of wood across them. Moving on to section 2, friend or foe, desirable versus undesirable friction. So here is the crucial takeaway. Friction is absolutely a double-edged sword. On one hand, it's incredibly desirable, right? It's the whole reason we can walk on the ground. It allows for power transmission through belts and gears, and it makes brakes, bolts, and screw jacks actually do their jobs. But then, on the flip side, it is highly undesirable in things like bearings and moving machine parts, where it causes this constant loss of energy and significantly drags down the overall efficiency of the machine. Just think about a brake pad clamping down on a rotor for a second. In that scenario, we are actively harnessing intense, aggressive friction to stop a heavy vehicle safely. We want as much resistance as we can get. But compare that to a power transmission system with a pulley belt. There, we have to carefully manage the friction. We need just enough grip so the belt doesn't slip right off the wheel, but definitely not so much that it creates excess heat and saps the motor's energy. It's a super delicate engineering balancing act. All right, section 3, static friction. Let's talk about getting started. Think about what happens when you try to push a really heavy desk across a room. The friction acting on objects that aren't moving yet is called static friction. If the force you apply is less than the force of that static friction holding it in place, well, that desk simply is not going to budge. You have to use extra force, crossing a very specific threshold just to get the stationary object to begin moving in the first place. You can really see the intense effort required here as the athlete pushes against that training sled. The red arrow shows the static friction pushing back with an equal amount of force. That athlete needs to exert a force greater than that static friction just to initiate movement. Until he breaks that barrier, he's just burning energy without going anywhere at all. But watch what happens next. The very millisecond that sled finally begins to slide over the floor, that stubborn static friction vanishes completely. It's instantly replaced by a totally different force acting in the opposite direction of the sled's intended motion. And that new force? That's what we call sliding friction. Which leads us perfectly into section 4, friction in motion, also known as dynamic friction. Engineers conveniently categorize dynamic friction, the friction of moving things, into 3 main types: sliding friction, rolling friction, and fluid friction. Each one of these has entirely different physical properties and completely different applications in the real world. So, let's break them down.
Let's compare two very different approaches to friction in motion. With sliding friction, ballet dancers will actually use sticky powder on their slippers to intentionally increase grip so they don't slip and fall. On the other hand, when an object rolls across the surface, like a skateboard does, it requires an entirely different engineering approach to keep those wheels moving freely.
And sometimes we have to manipulate sliding friction manually just for our own safety. Take a look at this super practical use, applying sand to an icy path. By introducing a rougher material between your shoes and that smooth ice, you are dramatically improving your footing. You're purposefully engineering a higher state of sliding friction to prevent a nasty fall. But when engineers want to make movement easy and efficient, they avoid sliding friction altogether and rely heavily on rolling friction. Why is that? Well, because for similar materials, rolling friction is significantly easier to overcome. It literally takes far less physical effort and energy to roll an object than it does to drag or slide that exact same object across the exact same surface. And this principle is exactly why everyday products like bicycles, roller skates, and skateboards use ball bearings. Engineers take these tiny, incredibly smooth steel balls and place them between the wheels and the rest of the product. So instead of two flat metal parts just grinding and sliding against one another, these small bearings roll between the moving parts, drastically reducing the friction and letting you just glide effortlessly down the street. Finally, we have the third type of motion-based friction, which is fluid friction. This happens when a solid object moves through materials that flow easily. And a quick reminder here, it's super important to remember that in physics, fluids don't just mean liquids like water or oil. Gases, like the air all around us, are also considered fluids. Now, just like rolling friction, fluid friction is incredibly easy to overcome compared to sliding friction. And this is the exact reason why solid machine parts, like the ones inside your car engine, are constantly bathed in oil. By introducing a fluid between the metal components, the solid parts move smoothly through the oil rather than aggressively sliding and grinding against each other. It preserves the machine and it keeps everything running efficiently. So I want to leave you with this final provocative thought. Imagine a world without this invisible force. How far would you actually get today without the static and sliding friction that lets your feet grip the floor? Or the precise rolling and fluid friction that keeps your car engine running and your wheels turning on your commute? Friction might steal some energy from our machines, but without it, our modern world literally grinds to a halt. Thanks for joining me on this explainer, and I really hope you walk away with a newfound appreciation for the incredible forces at play every single time you take a step.